So without going into any more detail, let's write down the answer for the three-dimensional box. So the three-dimensional box is a model of a particle in space. So an ideal gas, a molecule floating around in space, the center of mass of a molecule. And so this becomes a really physically meaningful model in the world now. And so the problem is exactly analogous to the two-dimensional one. We've already solved it. The energy is h bar squared pi squared over twice the mass, but now we have nx squared divided by L sub x squared, ny squared divided by L sub y squared, plus nz squared divided by L sub z squared. The three quantum numbers, nx is 1, 2, 3 to infinity, ny is 1, 2, 3 to infinity, and z is 1, 2, 3 to infinity. So any positive integer for any one of those three quantum numbers, and we're done. The wave function psi is now a function of x, y, and z of all position, and we can break it out in the separation of variables to a big X of x, big Y of y, big Z of z, and each of those is sine n sub x, y, z times pi and divided by L sub x, y, z times n x, y, z. So each of them is sine n pi x over L. Scaled by the appropriate length, and if the box is square, then the L's are all the same. And that's it. So that's how the three-dimensional box works. And as I say, that three-dimensional box is actually a very useful system. Now, one last thing I want to emphasize with the particle in the box and the two-dimensional box and the three-dimensional box turns out to be incredibly important. So do pay attention, please. I've constructed here a little MATLAB script and drawn the energy levels for a particle in a box. So here we have position. This is a box of normalized box, and the length is 1. Position on the x-axis here. The blue is the potential. We don't have little arrows, but we're heading up into infinity. And for the energy axis, I'm taking the energy divided by the energy of the first state, the first energy level, the ground state of the system. So for example, for the one-dimensional box, the energy goes just like n squared, or n sub x squared, and we're showing here the first 10 levels. So 10 squared is 100, so you see there's a level here at the top at 100. There's basically 1, 4, 9, 16, so we're just getting up toward 20, 25, just past 20, 36, 49, pretty close to 50 there. So they're the quadratically spaced levels. And you may not have had reason to be disturbed by this, but there's a bit of a weird thing going on here. The energy levels are getting farther and farther and farther apart. And that means the more and more energy we have in this one-dimensional box, the farther apart the energy levels get. It gets more and more obvious that there's this quantum spacing as you go to higher and higher energy. And that actually kind of violates a thing that we call the correspondence principle. Quantum mechanics is supposed to be something of the small scales. So it should be more evident when you have a tiny amount of energy rather than a huge amount of energy where what's the difference between one quantum of energy in me and the next quantum of energy in me? I have so much energy, you don't notice that graininess. And that's not actually obviously applying here. The energy levels are getting farther apart. Well, something really fundamentally interesting happens when we expand into multiple dimensions. And the thing is that if we go to even the particle on the square, the two-dimensional particle in the box, so if we go here to the two-dimensional problem, now I've drawn the energy levels. And it's much more complicated looking. And I've drawn up to, the maximum limit we have in the graph here is about 120. And the thing that's going on here is, let's say for nx equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, for that nx equals 10 case where there's an energy of 100 in the x, so that the x portion of the energy, if you will, is 100, the ny quantum number can take on any value, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so the ny increment of energy is 1 or 4 or 9 or 16 or 25, etc. So it fills in that space with a whole array of its own values. And so we fill the space much more completely. And now there's lots of energy levels. And if anything, you're getting more energy levels as you go higher and higher up, because all of those different ny values, if you will, are kind of piling on to the different nx's as you go along. So the space is getting richer as we go to higher energy, rather than poorer as we went to higher energy in the one-dimensional case. So now if we go to the three-dimensional case, where we have nx, ny, and nz all squared, now look at it. Now the energy levels are so dense as I go to even up toward 100 units of energy that you can see the quantum spacing down here for the first few energy levels. There's very, very few cases. And actually what I've done when I've drawn these red lines is I've slightly displaced I've basically added just a touch to the ny and the nz before I square them, so that the lines appear thicker. So you can see this thin red line is the unique ground state where nx equals 1, ny equals 1, nz equals 1. But the next up, I can have nx equals 1, ny equals 1, nz equals 2. So that's going to be 4, 5, 6, a total of 6 units of energy. But there are 3 different ways I can get that. I can have 1, 1, 2, 1, 2, 1, or 2, 1, 1. And they're all the same energy. There's 3 degenerate levels there, and I've drawn them at just slightly different levels so that at slightly different values so that the red line appears thicker. It kind of demonstrates that density. But even without that little trick, the density of states, which is exactly what we call it, is getting much larger, much, much, much larger as I rise in energy, as we now go even to one particle stuck in one now cube, which you can think of a unit cube of space for an ideal gas. And this is actually amazingly important, because as you learn about entropy, what entropy actually is, that magical quantity entropy, where we have the free energy of a system is equal to the enthalpy minus the energy times temperature, where the change delta G is equal to delta H minus T delta S. The entropy is actually, at the end of the day, as you'll learn about in physical chemistry next semester, it's a kind of accounting of the number of these quantum states that are available to a system. And so to some extent, the fact that entropy rises as energy rises in general is because there are many, 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 many more states open to the system at high energy than there are at low energy. And that very, very fundamentally influences the way that systems behave, down to why molecules dissociate if they're weakly bound. They're always bound. So if I can bring argon together with argon, and it actually would like to be by a small amount, it would rather stick near another argon. But there's only a few states that correspond to that, whereas the many, many, many states of a little bit higher energy that correspond to 2 argon atoms independently floating around in space at some distance from one another completely overwhelm the problem. And that's all about this fact that the amount of energy rises up as we head up in space. So when we look at the 3-dimensional particle in the box, we're not only using that as a fairly simple mathematical example of this thing we call separation of variables, it is really the model for the distribution of states, the energy distribution of states for an ideal gas. And it's really, really fundamentally very different from the one-dimensional particle in the box, because now this density of states is increasing dramatically as energy goes up. And that is just so very important when you get to statistical physics and thermodynamics and all of those fun things.